Hello. Today I'm going to present to you the techniques that I proposed in my dissertation for scaling 3D Gaussian splatting training. So as we all know, 3D Gaussian splatting has become a very promising new 3D primitive that could be differentiably trained for novel view synthesis. And similar to training neural networks, training such a model requires a huge amount of memory. As the volume of our scene grows, as with the amount of detail that are within our scenes, this requires more and more Gaussians to fully model the appearance of our scene. Yet, in order to start optimizing these Gaussians, we need to load them into graphical memory, which unfortunately is a very scarce resource, especially on consumer graphics cards. An intuition into making training large-scale 3D GS models feasible is in spatially segmenting the space we want to reconstruct, train submodels for each partition, and combine the results within each of these partitions. In our dissertation, we will call this general approach split and merge training strategies. Here we have a trivial example where split and merge training strategies would work perfectly. Imagine two rooms in which they're perfectly closed and they do not see each other, and they're separated by an infinite length. Given an initial set of Gaussians as well as a set of cameras, we could either train these two spaces jointly or separately as two different reconstructions. If we pick an arbitrary camera in one of these rooms, it would only see the Gaussians within its own room. In other words, the Gaussians in one room does not affect what the camera sees in another room. Therefore, if we're trying to use some camera to optimize our Gaussian model, it would only affect the Gaussians that are within the room, regardless of whether we're training these models separately or as a unified model. Therefore, the optimization problem that we're actually solving in both these models are actually identical. The same does not hold true when we have two submodels that actually can see each other. Say, if we merged the previous two rooms into one contiguous space, if we pick a camera and try and render only the side of the model it's on versus both sides of the model together, it might actually bear different results. As such, optimizing the model using one such camera would result in different parameters being updated, and therefore, this would make the two optimization problems different. This divergence of training objectives actually cause artifacts when we perform split and merge training naively. In this particular example, it actually causes the Gaussians on one side of the model to try and model for the appearance for scene geometry that should be on the other side of the model. And thus, if we perform the split and merge training strategy naively, we would actually accumulate in a lot of these errors and cause artifacts throughout our model. To formalize this understanding, we establish a term called visual dependency. Given two spatially segmented GS models that have their own set of cameras and their own set of Gaussians, if none of the Gaussians in one model could visually impact any of the images rendered by the cameras of another model, these two models are visually independent, and as a consequence, the Gaussians obtained from training both of these models separately and joining the results would actually be identical to training both of these models independently. Therefore, this allows for perfect split and merge training without any artifacts. However, once this visual independence is broken, if we forcefully perform split and merge training without any fixes, this would cause artifacting. Given this insight, we sequentially came up with 3 different split and merge training strategies such that we can train large scenes that don't fit into memory while avoiding artifacts. The first method that we propose is using graph cutting methods to find visually independent submodels. The idea is if we want to effectively split and merge our training process, we need to find submodels that are visually independent of each other. As an example of how this might work, here is a sample structure from motion reconstruction of an apartment with multiple rooms. It consists of a bedroom, a corridor, and also a washroom. Intuitively, we might want to decompose a scene into subsets using these rooms. This is because each room only has a small opening in which the cameras in one room can see into the geometry of another. So while these submodels aren't perfectly visually independent of each other, it serves as a good enough approximation and probably is close to the optimal solution. Yet to a computer, this division may not be apparent if we just look at the low-level data. Given any two pairs of cameras, we could quantify their visual dependency using the projected area of the shared geometry within these two photographs. We could further approximate this metric by using the number of shared features within the photographs. Now that we can calculate the visual dependency between any pair of cameras, we can then form a graph that depicts how well connected each camera is, where the edge weight quantifies how visually dependent each camera is to each other. Now, these rooms are actually reflected on the topology of this graph. Pairs of cameras that share the same room should have a much stronger connection compared to pairs of cameras that are in different rooms. Now, using graph cutting methods, we can recover individual groups of cameras that are better connected to each other, such that we minimize the visual dependency between these groups. We can then recover the Gaussians for each group by choosing the visible Gaussians for each group of cameras. By applying this technique to this example, we find that it is actually able to recover the groupings that we were expecting. However, there are still these residual visual dependencies between each groups, and in our empirical experimentation, we find that these visual dependencies still cause significant artifacts during split and merge training. Thus, this method really only works well for the small amount of cases in which perfectly visually independent submodels can be found. For a more general solution, we came up with our second method, loss masking, which theoretically allows for the split and merge training of visually dependent submodels while not causing any artifacts that we've previously seen. In order for loss masking to work, our scene needs to be divided using a mutually exclusive and collectively exhaustive partitioning of Euclidean space to divide our Gaussians, where cameras can be arbitrarily and non-exclusively distributed between groups. Given a camera in one submodel that is visually dependent on other submodels, the ground truth image of the camera actually sees part of the scene that should not be modeled with the Gaussians within its own submodel. These parts of the regions are what's causing the artifacts, as previously demonstrated. The idea of loss masking is that if we know the geometry of the space that we're looking at, we could actually mask out the areas of the image that should not be modeled by the Gaussians within our own submodel. Subsequently, we can use this mask to modify the loss function such that areas that are masked out do not receive any loss propagation, and thus our Gaussians will not overfit into these regions in which it should not model for. With this modification, we've effectively removed the visual dependencies on a pixel-by-pixel level. Subsequently, this would allow us to perform split and merge training without the artifacts that we've previously seen. However, the question remains on how we can obtain the loss mask, which will be used to modify the training process, since it requires an understanding of the underlying scene geometry. For this, we train a global coarse model for our entire scene. By only using 1/100th or 1/10th of the actual Gaussians we need to use for the final model, we could actually train a coarse global model that successfully models the geometry inside of our scene, but sacrifices on the textures of surfaces. However, here we are only concerned about the geometry of our scene, so this model will be sufficient. We can then further determine the loss mask for a particular camera by coloring the Gaussians belonging in the current partition white and Gaussians belonging to the other partitions black, from which we render our coarse model from the viewpoint of our camera. To evaluate the efficacy of this method, we trained models using the same dataset as the Gaussian splatting paper. Over the 9 scenes in which we trained models on average, we see a 66.5% reduction in graphical memory usage, while only receiving a 9.5% reduction in PSNR quality. Qualitatively comparing the results of this method compared to regular 3D Gaussians, as well as a baseline split and training method that does not use loss masks, we see that our results manage to recreate the results of 3D Gaussians much more closely compared to the naive method. However, this technique introduces its own set of problems. On memory usage, while the coarse model uses much less parameters compared to the full model, it still scales linearly to the volume we want to reconstruct, rather than constant scaling of the naive method. So while it does allow for the training of larger models that were previously impossible, it still does not allow for training arbitrarily large scenes. Regarding the quality of our reconstructions, our global coarse model only manages to create an approximation of the actual distribution of geometry on a pixel-by-pixel level. The mask should only produce black or white values, whereas the ones produced by our coarse model has blurry boundaries instead. Moreover, these loss masks only work correctly under the assumption that a single pixel value is only responsible by the Gaussians of one partition at one time. This fails when we see a pixel in which we see contributions from both translucent Gaussians within our current partition, as well as some Gaussians from other partitions, in which it actually happens quite frequently since Gaussians are translucent at its edges. Therefore, loss masking actually introduces its own sets of artifacts, especially near the seams of merged submodels. To address these problems in both memory usage and quality of our reconstructions, we came up with our third approach called submodel compositing. Let's review some of the algorithms that we've mentioned so far to inform how we can develop this new algorithm. Suppose a camera sees 3 subsets of spaces, each having their own objects, of which these objects could occlude each other from the camera's point of view. In this diagram, the cylinders that you see represent the Gaussians that form a 3D model of our object in our scene, whereas the arrows represents the rays of light from the camera's ground truth image, in which we use to optimize our Gaussian model. In regular Gaussian splatting, we can see that our 3D Gaussian model matches up well with the camera rays projected by the ground truth image. In naive split training, say if we're only optimizing the parameters in the central partition, the 3D Gaussians of the other partitions of the model are no longer present. However, since we're still using the same training image unmodified, we now have camera rays from our image that correspond to non-existent geometry, subsequently causing artifacts. Loss masking simply tries to filter out these rays according to its understanding of scene geometry, but suffers from the issues that we mentioned earlier. With submodel compositing, instead of just removing out-of-partition geometry, we could emulate the presence of the Gaussians in the other partitions by using a pre-rendered image from the same camera. Then, these different layers could be combined together using standard alpha blending. The images of the other layers are not optimizable parameters, so effectively, it's like we're only focusing on optimizing the parameters within our central partition, while the parameters of the other partitions become this frozen model. Moreover, for these frozen partitions, we don't really actually need to load the parameters into graphical memory. Instead, it's just one single photograph. Compared to loss masking, the content in the other partitions are fully accounted for and alpha blended just like how they would be if they were actually there. Therefore, artifacts to do with translucent objects that we previously mentioned should no longer be an issue. However, the question remains on how we can get the pre-renders of other partitions if we're only starting with one partition. We would not want to use a global coarse model for this because of the scalability issues we previously mentioned. To solve this problem, we propose using interleaved submodel training. Instead of fully training each submodel sequentially, we will switch which partition we're actually optimizing on a predetermined interval. By doing so, each model builds up a better and better picture of how their neighbors look over time. Here, we demonstrate an implementation of this algorithm in action. On the left, you have a real-time view of the image used for loss calculation. At any time, this camera sees all the Gaussians within all the submodels, since they're always composited together. While on the left, you see the view of the actual Gaussians loaded as a 3D representation. This method still has its issues, but it's much less severe. One of the bigger issues is that the number of images we need to communicate and store would increase quadratically. A potential optimization we can do is in assuming a submodel wouldn't be visible after a certain distance from the camera. By doing so, we limit our storage requirements back to being linear to the volume that we're trying to reconstruct. We believe that this approach of training Gaussian splatting is very promising, and it's also very transferable to other differentiable novel view synthesis techniques such as NeRFs. If in further testing we could actually see that this scales really well into larger scenes, we shall move on to the next hard problem of scaling Gaussian splatting, which is how you can render such giant models at interactive rates on hopefully consumer devices or even mobile phones or VR headsets. Thank you for your time, and I hope you like this presentation.